I have started the recording. Okay. Then further we see that like how the reflection depends on wavelength, angle of incidence, okay, and surface roughness. So let me share the PPT through which I will start my discussion. I hope you can see the shared screen.
Yes, sir.
Yes, sir.
Okay. In the previous lecture, we have already discussed about how the electromagnetic radiation interact with the Earth surface object. And once again, briefly, I would like to revise the discussion we had previously. So in this case, this EI is the incident energy. Okay, so it interact with that at this particular junction, okay, over here. Then what happens? This medium is air. Okay. Now this EMR radiation goes from air to liquid. Okay. So when this goes from air to liquid, okay, so part of energy that is reflected back is ER. Okay. Then ET is transmitted, because see, within the liquid, EMR radiation travels up to certain extent. Then EA is the absorbed component. Okay. But let's say if energy EMR radiation is moving from air to solid, so in this case what happened? Then in this case we can say that this transmitted component is nearly zero. So we have only two components, reflected component and absorbed component. Okay. And these are the function of wavelength. It means this is the function of wavelength. It is equal to E absorbed plus E reflected. Okay. Now we need to normalize it. So you need to divide this equation, that this is equation first. So divide this equation by the incident energy. So in the left hand side, you have 1. It's 1 is equal to, now in the right hand side, if you divide reflected energy by the incident energy, then you will get let's say I use term alpha over here. Alpha is I'm using for the reflectance, okay, plus again this beta I'm using for absorptance, okay. So alpha is the ratio and it varies from 0 to 1. Fine. Similarly, beta, it is also a ratio and it again varies from 0 to 1. Okay. Now let's say what happens when beta is equal to 0. Who will tell me? If this beta means it's absorptance. Beta here I'm using for absorptance.
Total energy will get absorbed.
If see beta is equal to 0, it means there is no absorptance. And considering the equation 1, that is a result of law of conservation of energy. So we can say that
The beta is reflectance or
2 times I repeated beta is absorptance, alpha is reflectance. Should I write over here?
okay.
So from your side, sound is little bit slow.
Is it the case for all of you?
Yes, sir. Sometimes stop
Yes, sir.
sometimes.
See, I'm speaking very louder.
Yes, sir. Voice is very low.
So alpha is reflectance and beta is absorptance over here. Fine. So beta is absorptance. Okay. So alpha reflectance, beta absorptance. If beta is equal to 0, then what does this mean?
Specular reflection. Total 100% reflection. Energy coming or reflection.
Don't combine over here. Specular and diffuse we'll discuss later. That is not a case over here. If beta tends to 0 means the entire energy that is that incident at this particular interaction point, that is totally reflected back. Okay. And when alpha is equal to 0, in that case what will be? Beta is equal to 1, though it is not, it is the ideal case. In practical scenario we don't have such kind of alpha and beta combination. So in ideal case, if alpha is equal to 0 means that material at which this energy is interacting, okay, so that material completely absorbs the total incident energy. Okay. So we have 3 important points, like the proportions of radiated, absorbed and transmitted vary for different earth features depending on their physical, chemical and biological characteristics. Okay. So what does this mean? Because there is a dependency on the wavelength. When we write this equation, this is equal to ER plus EA plus ET. Okay. When we write this equation, the proportion of ER, EA and ET, that proportions are dependent on the wavelength. Okay. Why it is so? Because once at a particular wavelength, that energy, let's say this is the incident energy, and it interact with this particular point. Okay. So what is a component of ER, EA, and ET? Okay. So that proportions depend on the material property over here. Okay. And if you change the wavelength, there are two. If you change the wavelength, these proportions again change. Okay. Let's say I will ask you a question. It's a logical question, and I hope you respond it. Let's say at a wavelength lambda is equal to lambda 1. This is a fixed wavelength. Okay. And we have a certain so at lambda 1 there are the specific contribution of ER, EA, and ET, and some of them is equal to EI. Okay, ER, EA, and ET at lambda is equal to lambda 1. Fine. Now, based on the discussion at point number 1, I'm going to plot a curve between the reflected energy and wavelength. This is lambda, okay, and this is ER. It's a reflected energy. Fine. So at lambda is equal to lambda 1, let's say ER can be written as ER at lambda 1. Okay. So that is a range, and this is indicate ER, the reflected energy at wavelength lambda 1. Fine. Somewhere here we have a lambda 1. So for this lambda is equal to lambda 1, this is one particular point. I can say this is the location, like at lambda 1, we have the value ER lambda 1. Okay. But for the rest of the wavelengths, in addition with lambda 1, let's say for this, there will be two ranges. This range is lambda is greater than lambda 1, and this range is lambda is less than lambda 1. Okay. I'm just making this ER as a kind of step signal. Okay. Whether lambda is less than lambda 1 or lambda is more than lambda 1, ER is equal to ER lambda 1. Is it true? Kindly let me know if you want me again to like explain this problem.
Yes, sir.
What you have not understood, then that point only I will discuss.
So you say the lambda is less than lambda 1 and lambda is more than lambda 1. And sir, the lambda r is equal to lambda r lambda 1. Sir, I just confused between what I need to just tell you about the question. What's the exact
Okay.
one?
Okay. Let me again discuss the point I discussed recently. The point number 1, the proportions of ER, EA, and ET. It means let's say I select EI as a particular, let's say, decimal number 10 unit. Okay, EI is selected as 10 unit at a particular wavelength. Let's say lambda is equal to at lambda 1. Okay, now this 10 unit is distributed into ER, EA, and ET. Okay, in the format of 2, let's say plus 4 plus 4. Okay, so let's say 2 is the reflected. Okay, it is absorbed, and plus it is transmitted. Fine. What happened if we do the same analysis? If we do the same analysis at another wavelength, let's say lambda 2. Okay, so at lambda 2, what will happen? Obviously, this EI will be a different figure in that case. Okay, when EI will be the different figure, let's say it will not be 10, it will be some different value. Let's say it is 12. Okay, now when it is 12, and if you correlate, like in case of 10, it is divided in the form of 2 plus 4 plus 8. 2 plus 4 plus 4. Like if you divide it by 10, if you normalize it, it will be 1 by 5. Okay, now it will be 2 by 5 plus 2 by 5. Okay, so whatever the magnitude of EI is there at lambda 1, it's 1 by 5th. Its fifth part is reflected energy, 2 by 5th part is absorbed energy, and 2 by 5th part is transmitted energy. Fine. Now we have at lambda 2, the EI will be different. Now can we say that in the same form, like 1 by 5, 2 by 5, and 2 by 5, it will again be divided? If it will be, then what you write over here? 1 by 5, 2 by 5, and 2 by 5.
No, sir.
So it will be 12. So I think 12 divided by 5. How much it will be? 2.4, correct? Plus it will be 4.8, plus it will be 4.8. See, this will be the case only when at lambda 1 and lambda 2, the material behaves same. Okay, but what happens due to different physical, chemical, and biological characteristics? These characteristics are dependent on the wavelength, because the way they respond to the incident energy, okay, to divide it into 3 different components. Okay, when you change the wavelength, what will happen? Their response, the way they divide it into 3 parts, changes. Correct? So in this case, there might be a possibility in a different proportion that 12 is divided into 3 parts. It could be 6 plus 4 plus 2. Is it okay?
Yes, sir.
So if now it is divided into 3, 4, and 2, it means, now see over here, at lambda 2, the reflectance is dominant. At this particular wavelength lambda 2, from the same material, reflectance is dominant because we are getting 6 over here, highest. While in the previous case, absorptance and transmittance are dominant. Okay, at lambda 1. Why it is happening? It is happening due to the difference or different response of the material at a different wavelength. Okay, and see, this is the region, this is one of the important property that allow us to do the remote sensing. If the response will not change, let's say if the response will constant, okay, like irrespective of the wavelength, the incident energy is divided into equal proportion. Okay, so in that case, what will happen? See, in this diagram, better we can take the normalized value. Normalized value means we take the ratio. So, like for EA, what value I derived? What is the ratio for this? That is alpha I took. And if it is solid, then absorptance is zero. Sorry, this transmittance is zero. So we have absorptance component. For it, we have a beta component. Okay. If I write alpha over here, okay, so I hope there is not a confusion regarding this ratio. I'm please just see over here. Okay. Equation 1, divide it by the incident energy. Okay, you will get this ratio. This is 1 is equal to alpha plus beta, where alpha is reflectance and beta is absorptance. Okay. So I'm discussing this point number 1. Let's say if we consider ideal case where the proportion in which the incident energy is divided by the material into 3 parts is independent of the wavelength. What will be the alpha versus wavelength curve over here? Please tell me. What it will looks like. I hope you have understood the query. Praveen, could you please unmute? Praveen Kumar.
Yes, yes, sir.
What we are discussing over here?
Sir, graph will be plotted each parallel to wavelength.
No, correct. See, just I would like you to participate in the discussion. Okay. So
Yes, sir.
previously what we discussed corresponding to point number 1. Okay. We talk about how the response of a particular material. Okay. Whether it is, if we talk about earth surface object, so it could be building, it could be a road, it could be soil, it could be vegetation. Okay.
Yes, sir.
So the electromagnetic radiation that incident on, let's say, soil, fine,
Yes, sir.
and it is after the interaction with the soil, it divided into 3 parts of energy: absorb,
Yes, sir.
emitted. Okay, but
Sir, it
soil
will
is the
depend
solid
on.
medium. So what? Yeah, please proceed. You want to say?
Sir, if, mm,
You can try. No issue.
incidental,
Like I will help you to respond it correctly. No issue. Whatever you know, you can discuss.
sir, incidental energy मतलब depend on the material and wavelength. तो अगर सर जो मतलब ये ट्रांसमिट हो रही है अगर मतलब 3 पोजीशन में तो अगर वो डिपेंड करती है सर मटेरियल पे ही और वेवलेंथ पे अगर
हाँ, मीनिंग ये है कि जो इंसिडेंट एनर्जी है, okay, it is after the interaction, it is redistributed into 3 different form. Okay,
yes, sir.
so that is EI is equal to ET, EA, and sorry, reflected,
ER
absorbed, and transmitted. Fine.
transmit. Yes, sir.
So EI, see magnitude of EI at the Earth surface point where it interact with the material. यहाँ पे हमने soil
Yes, sir.
select किया है, तो at a particular small area, soil की small area पे जब EI energy fall करती है, okay, so in that case EI magnitude depends on how much energy transmitted from the sun and how it goes through the atmosphere. But finally, the energy that reaches to that particular soil location, it is divided into three different form of energy: ER, EA, and ET. Though it is a soil is solid, so we can say that the transmitted component is nearly zero. Correct?
Yes, sir. Yes,
We
sir.
have only two components, reflected and absorbed. Fine.
Yes, sir.
So when we take the ratio, when we divide it, as you see previously, when you divide it by EI, both sides of this equation, then you will have a ratio. They are the variable alpha and beta you will get.
Yes, sir.
So again, this alpha is the function of wavelength and beta is the function of wavelength. Fine.
Yes, sir.
Okay. And I told
Yes, sir.
that with respect to point 1, okay, with respect to point 1, the value of alpha and beta changes with respect to wavelength. Why it is so? क्योंकि यदि हम दूसरे वेवलेंथ पे एनालिसिस करते हैं तो ये जो इसका रेशियो प्रोपोर्शन में जो हम ऐड कर रहे हैं, रिफ्लेक्टेड एंड एब्जॉर्ब, ये प्रोपोर्शन चेंज हो जाता है एज आई डिस्कस बाय दिस एग्जांपल ओवर हियर. Okay, like in the previous case, 10 is divided 2 plus 4 plus 4 at lambda 1. If you normalize it, then 1 is equal to the reflected is
1 by 5.
Yes, correct. Fifth part.
1 by 5. Yes, sir.
And the next two are 2 by fifth part. Okay.
Yes, sir.
But in the same proportion at a different wavelength, it divided. Okay, why it is so? Due to the internal composition, chemical, biological property, if wavelength changes, the material property to divide energy into three different forms changes. Correct? So now just see in the second case, it is 6 plus 4 plus 2.
Plus 2.
Now what will be the proportion in this case? 1 is equal to, it's 1 by 2 now, plus 4 by 12. So we can write it 1 by 3, is it? Plus 1 by 6. Now just see, at lambda 1, the division is fifth part, 2 by fifth, 2 by fifth, but at lambda 2, energy divided by half, third part, and sixth part.
Third part.
Got it?
Yes,
so now the query is, if I plot wavelength versus alpha curve, okay, and if I drawing it as a strip signal, this is strip signal, is it correct?
Yes, sir. Alpha is parallel to wavelength or value is 0.5.
Who will tell me whether the step signal which I am drawing, the alpha variation is constant at all the wavelength? Is it correct?
No, sir. Material will be changed to alpha. Alpha vary करेगा, sir.
Good. That I this response actually I want to listen from your side. Good. See, because at 2 sample point we have already tested it. Just see here it is 1 by 2, while in this case it is 1 by 5. Okay. So if we consider only this 2 sample point, then what will happen? Even at lambda 1 location and lambda 2, I think I have selected if lambda 2 is more than lambda 1. So it could be somewhere here. It's lambda 2. So at lambda 1, what value we are getting? We are getting 0.2, is it? Let's say somewhere here we have 0.2, but here we are getting 0.5. So this will be curve like this. So this curve indicate that at if you change the wavelength, then alpha value will change. Then further, what does this mean? You can mute yourself.
Thanks.
Thank you. So again, I'm going to discuss with you why it is important for the remote sensing. Why this property of material? Okay, that tells us that okay, if we change the wavelength, then the reflectance will change. How it will help you for the analysis, okay, for better understanding of images, okay, and how it is very useful for the remote sensing. Okay, very carefully listen. I'm connecting all the concepts together. Okay, in the books you will get a straightforward like the concepts, their analysis. Okay, but these are totally different analysis. Okay, we are combining all different fundamentals and background. Okay, um, the analysis is being done. So, and I hope parallelly, as I suggested before, you are making a note. So I expect you, like you have a notebook for this course, and with the discussion you are writing in your notebook. Okay. So based on our discussion, point number 1 and 2 both, I think the point number 2 they talk about these energy are wavelength dependent. This part. Okay. So this energy is wavelength dependent. It means if wavelength changes, then in that case there is change in wavelength, alpha change. I suggest you once again kindly revise the discussion we have. Okay. Then after I will further discuss this the next concept. Okay, take your time, 5 minutes. Revise the discussion we had. Okay, and let me know if you have any small, even very small query. Okay, no need to hesitate. You can discuss with me.
Hello, sir.
Okay, is there any query?
Sir, shouldn't we first talk about the surface on which the wavelength is radiated upon to plot graph between lambda and alpha beta to get any meaningful graph,
Like in case
like
when we consider, yes,
water
when
body, vegetation, soil.
yes, when we consider the entire globe, okay, so the objects which are present in majority, they are water, okay, and we if we consider the landscape, then we have a vegetation, green vegetation, okay, we have a soil, we have a snow, okay, we have a sand. When we consider the concrete, like the building rooftop, then we have a concrete. When we consider the road, then we have a bitumen. Okay. So when we select these objects and we plot the reflectance with respect to wavelength, okay, so there will not be a kind of step signal. Step signal means there is no change in reflectance with respect to wavelength. Okay, we get a variation, like when we change the wavelength, then the reflectance will change, like in this case. Okay. Let's say assume it is a kind of simulated where it's a simulated plot for a particular object where alpha changes with respect to wavelength in this way. Okay, the way it is plotted in the graph. Fine. And I told that considering the point number 1 and 2, okay, this change is required for the remote sensing. And it is very important property. Why it is so? Let's see over here. Let's say at the satellite, we have two sensors, sensor 1 and sensor 2. Let's say sensor 1 is designed at the frequency 0.5 micrometer. Okay. While the sensor 2, that is S2, it is designed at, let's say, 1.4, 1.5 micrometer. Okay. So 1.5 micrometer, it's a central frequency, and there is certain bandwidth corresponding to these two sensors. Okay, S1 and S2. It means these sensors are only looking. S1 is only looking into this band S1. Okay, while S2 is only looking within this. Fine. Now let's say we have a landscape, and for this landscape, satellite imaging is performed. And what it does, first it divide the area into the grids. We have already discussed it before. Okay, just see over here. This is plot for a fixed material. Let's say it is for M1. For material M1, the alpha versus lambda plot is drawn over here. Okay. And but let's say somewhere here this is M1 is present. For all these locations, the material M1 is present. Okay. When this is sensed by sensor S1, just see over here. The risk is very low. It is around 0.4. Okay. So when it is, but the same material when it is sensed in S2, see the reflectance is 0.6. What does this mean? In case of S2, more energy is reflected back compared to S1. But it means the energy sensed by S2, there is other parameters also, like if this in case of S2, this is higher than S1, the wavelength is lambda 2 and lambda 1, let's say. So this lambda 2 is more than lambda 1. So there is also factor, like at a higher wavelength, the photon energy will be less compared to lower wavelength. So that will also come into the picture over here when you are quantifying the total energy coming out from that cell. Okay, but based on this analysis, you can say that the energy coming out from all these grids, which are comprised of material M1, okay, in case of S1 and S2, that energy will be different. Are you agree with me?
Yes, sir.
Okay, it is very obvious, no? Like when this reflectance is different, so less amount of energy is reflected in S1 band, but while in case of S2 band, proportion, if you talk about proportion, so then the large proportion is reflected back. Okay, so in this way, in band S1 and S2, energy coming from the same material, the energy coming from the same material is different. Okay, if they are different, it means the corresponding digital number that is assigned, okay, for material M1, the digital number will also be different. So just see, material is same, but that material, when you change the wavelength, the behavior of that material is changing. Okay, it means more information is released by that material. It is like when we talk about if we want to identify a particular person, okay, so just see more number of information we want to gather, like what is height of that person, okay, and what is the physical appearance of that person, okay, what is the shape of the face of that person, okay, similarly, okay. So dimension is one parameter, but the dimension of a different part is different. It means the information content is more. So when you are going to increase the information content, precise or accurate detection of that person will be high. Like in a dimension, if you are going to divide it into like height, then face shape and size, okay, and what is a physical appearance of that person. If you keep on increasing the information content about that person, then there is a high probability to identify that person. Okay, in the same line over here, if you see, if you are changing the wavelength, it is an inherent property of material. Like a person has an inherent property, different shape and size, different face, like that, like face, different shape of the face. Okay, so a person is totally different from other person. Okay, and there are a lot of physical properties. Based on that, you can just identify that person. Okay, now it depends on you how you could able to extract all those information. If information will be high, there is a more likelihood, or there is a high probability to identify that person. Okay, similarly over here, when wavelength changes, different reflectance we obtain. Okay, this is the inherent property. Now it is a capability of your system how that system can exploit, I can use all these, can record all these information that is conveyed, that is shown by the objects. Okay, and just see over here, one part I am discussing over here. If you change the wavelength, the behavior of material is changing. So if you keep on adding the bands, just let's say S1, S2, S3, S4, S5. Okay, if you keep on adding the band, and if you keep and if you analyze the reflectance behavior of material at a different band, at a different wavelength, okay, it means you are just utilizing the information that is already there with that material in terms of its reflectance. Okay, so this is the reason why, on the basis of number of bands, so this part I will take later on, but briefly I discuss over here. On the basis of number of bands, we divide the remote sensing technique into three parts, satellite imaging technique into three parts. The first one is panchromatic. Okay, panchromatic satellite imaging, we use only one band. Okay. Then the second one is MSS, multispectral sensor. We use 4 to 12 number of bands. Okay. While the third one is hyperspectral. Okay. Third one is hyperspectral remote sensing, where we use 100 to 200 number of bands. Okay. See, when we use such large number of band, then in that case, we can say that in hyperspectral sensing, when we process these large number of band, in that case, we can go for subclasses identification. Like even within the vegetation, there are subclass of the vegetation that can be identified. Why it is so? Because very small changes even can be identified, can be recorded in these large number of bands. Okay, though this part I will discuss later on.
सर सर अगर बैंड 2 है तो उसको किस में कंसीडर करेंगे, पैनकोमेटिक में कि एमएसएस में?
More than one, it will be MSS, but generally we don't have band 2 number of band.
सर जो आपने पहला एक्सपेरिमेंट कराया था विजुअलाइजेशन वाला, तो उसमें TMB1 TMB2 था, सारे बैंड के डिफरेंट इमेज थे, तो क्या हम उसको ऐसे रेट कर सकते हैं जो TMB1 था पैनकोमेटिक था और उसके बाद ऐसे
नहीं, that's why I told you in the laboratory, kindly go to the detail of the data sets. Okay, in that particular satellite imaging program, more than 4 number of bands were in more than 4 number of bands images were required. Okay, so multispectral sensors were used. Okay, and if you see the TMB1, TMB2, TMB3, TMB4, there are many bands. Okay, so generally we don't have 2 to 3 number of band. Three band, it means it's a kind of digital camera. The digital camera, we have a 3 band, red, green, and blue. But generally, if you see the existing satellite imaging program. Okay, so the satellites, they use more number of 4 bands, 4 bands in MSS, while in panchromatic we have a single band. Okay, so I hope there is no any query related to the EMR interaction at the Earth surface point. So this discussion we have related to we go back. The step C we are discussing right now. Earth surface features, how that energy interact and what is the response. Okay, and the source of energy, this propagation through the atmosphere, retransmission through the atmosphere, this part we have already discussed. Now just see in the image, from the same area, in the first case image is acquired in green band, while in the second case it is acquired in infrared band. Now see the grayscale image and the difference. Okay, so images are different. It means the different DN numbers are assigned. Now this third point, when we talk about interaction at the Earth surface point, so that is a geometric manner in which energy is reflected is also important for the remote sensing. Okay, and here we can see that how energy is reflected back. Okay, so there we see the effect of wavelength, that is lambda. S is the surface roughness, and we also include this theta. Theta is the angle of incidence. Okay, at what angle this is theta? Angle of incidence. Okay, we'll see the effect of theta, wavelength, and surface roughness in the type of reflection that takes place from the Earth surface. Okay, now see the first case. It is a perfect specular reflection. Okay, it takes place when wavelength is very large compared to S, surface roughness. Surface roughness means, just see, this is a grid over here. Within the grid, let's say we are selecting a particular point. How point can be defined? Let's say this is the interaction point. So that interaction point, let's say this has area A. When we say A tends to 0, okay? A tends to 0 means now it is a point. Okay? So let's say that is the point which we are talking about, this interaction point. Okay? And we can say that this interaction point A tends to 0. Fine. So energy is incident on this interaction point, and part of energy is reflected back. Fine. When at this point the wavelength is very large compared to surface roughness. So I would like to discuss what do you mean by surface roughness over here. Okay. This is the small area that we are considering A tends to 0. Okay. If we see that, if we consider it as a mirror, okay, so mirror, we can say that it is very smooth and flat surface. And let's say if we consider the soil, okay, so in the soil you can see that we have differences in the height. Like if I analyze, if you see that this is They are the ABCD are the four vertices of this area A. You see from the side. Side means this is the side view I'm talking about. This is A, B, this is D, and when A and D coincide, and this is C. This is the side view. When you see from the side, in case of mirror, it is a kind of straight line. Okay, you can see the straight line. But if it is sand or soil, so in that case, you can see some elevation. Some part is lifted up, while there is some small valley, you can see. So this is called as rough surface. It's not smooth like mirror, it is rough surface. And when we take the difference in height, S is computed as just this standard deviation of height change over here. So the changes in height in terms of standard deviation is estimated in form of surface roughness S. Okay. So now see over here, wavelength is very large compared to this roughness S. Okay. In that case, what will happen? We get a what kind of reflection we get? Sunil, could you please unmute?
Yes, sir.
If wavelength is very large compared to surface roughness S, then what type of reflection we get?
Specular.
What do you mean by specular reflection?
It means surface is like mirror
Correct.
and angle of reflection is equal to angle of incidence.
Correct. Angle of reflection is equal to angle of incidence. It Snell's law apply over here. So along the angle of reflection, all the energy is confined within a line. Okay, it is not divided
Okay.
spatially. You can mute yourself. Thank you.
Okay.
So in a particular line, the energy that is falling on the surface, it is reflected back following the Snell's law, where angle of incidence is equal to angle of reflection. In a certain direction, it goes in the atmosphere. It goes into the medium. Okay, but what happened when this inequality will fail? This inequality will fail. Let's say if this is like that. Okay, this will fail when S is constant. It means same material, but what happened? You decrease the wavelength. Okay, if you keeps on decreasing the wavelength, then what will happen? In that case, at the smaller wavelength, what is happening? The perfect specular reflector. Previously, the surface with surface roughness S that behaves like a perfect specular reflector. When you start decreasing the wavelength, it starts behaving like a near perfect specular reflector. Okay, where the reflected energy is not confined along a particular line, but now it is divided spatially into different directions. See over here. Still, the dominant energy is along the line that follow the Snell's law. Okay, but still you can expect a component around it. Okay. Now further, when the reverse will be true, for the same material, is again you are not changing. but you keep on decreasing the wavelength, and let's say if it is satisfied, material same, just see that I'm not changing the material, it is same, but you have decreased the wavelength up to the extent where this inequality is satisfied now, where wavelength is very less compared to the surface roughness. So in that case, what will happen? There will be a diffuse reflection. It means at this particular point where we say A tends to 0, okay, the energy is reflected back into a half hemisphere. Okay? In all direction, it is reflected back. Okay, and actually for the remote sensing, we require diffuse reflection. Who will tell me why?
Sir, maybe it's uniformly distributed in all directions.
And it also color information, spectral information. Color.
Could you please speak louder?
Sir, due to rough surface?
Uh,
Sir,
mhm.
just uniformly distributed in all directions. This why in remote sensing we consider this.
But see, if we compare with the specular, then obviously in case of diffuse, the return, if we talk about the energy within the reflected component, is less. But see, in a particular line, all energy is reflected back, while the same energy is over here redistributed in all the directions. So why you are giving weightage to the uniform distribution? I mean this
Sir,
uniformly.
because sir, diffuse reflection, we get to know more about the surface, more spectral information about the surface than specular.
This I'm leaving to you, and I expect you to explore it. Just see whether sun target and sensor geometry we consider over here to for this. Is there any role of that? Okay. So I hope you will explore about it, why it is so, and okay. Now to a mathematical equation over here, we see how the we have discussed about the surface roughness and wavelength. Okay. So there is also factor theta, that is the wavelength. Sorry, this angle of incidence. So HT is indicating the surface roughness over here. When it is less than or equal to lambda, okay, divided by 8 cos theta. It means surface roughness is less than, if it is satisfied, it means if we compare surface roughness and wavelength, okay, so in this case we can say that we are considering the surface roughness less than wavelength. So what kind of uh, reflection we consider over here? It is this inequality is satisfied. I want a response from you. And this inequality is satisfied, then what kind of reflection takes place? See, always you need to remember, like when we compare wavelength and surface roughness, wavelength is considered higher than surface roughness. Okay, so in that case, we have a specular. We call it Rayleigh criterion. Okay, is surface enough rough to have an interaction? Interaction means we have a enough roughness in the surface so that we can obtain a diffuse reflectance. That we consider in the remote sensing. Okay, so if HT is less than, it means we compare. Let's say this is a constant over here, and what we can say that we can say that okay, this HT is less than wavelength. So wavelength is high. It means that compared to roughness, it will support a specular reflectance. Okay, and when you increase, when it will furthermore, what you can do, let's say if you decrease the wavelength, okay, if you decrease the wavelength, then what will happen? It will be diffuse. So just see over here, at a fixed surface roughness, at large wavelength, it is specular, while at short wavelength, it is diffuse. Okay, so while considering the design of sensors, we also consider this part. Okay, so there are 3 points. There are 3 important points. The first two talk about the variation of different composition of energy with respect to wavelength. And now the third point is in the geometrical manner in which energy is reflected back. Okay. Just see over here, it is given like this H is the surface roughness. It means this is a variation, a standard deviation of this height is measured. Okay. And this is the theta, angle of incidence. When we consider the wavelength, that is lambda. Okay. If it is greater than or equal to HT to 8 cos theta. If wavelength is greater than HT cos theta, in that case, what you will have? Wavelength is larger, then we'll have a specular. Okay. For the given HT, if you want to have a diffuse reflection, what you need to do? You need to decrease the wavelength. Okay. Or what you can do is, you see the variation of cos theta, and this is cos theta. This is 0, and let's see if I consider this is 90. 0 value is 1, 90 it is 0. Okay. So this inequality will also change. If we imagine the Earth's surface, whether it is midday or it is sunrise or sunset. So see, when you are going to imaging a surface while sunrise or sunset, in that case, what will happen? Theta will be large. It will close to 90. While midday, we can say theta can be equal to 0. Okay. When theta will be 0, like when this is sun, as sun is just above that surface. Like if sun is over here, okay, in that case theta is theta is 0, then in that case is cos theta. Fine. But when you move towards theta larger value, then it decreases. Okay. It decreases means what will happen in that case? If it decreases, then always this inequality will be satisfied. Okay. And if you want to go for diffuse, what you need to do further, you need to decrease the wavelength. Like it can be written, if you want to change this inequality to move it from specular to diffuse, this is the change required, delta lambda 1, to make it specular to diffuse at, let's say, theta is equal to theta 1. Okay. Now when theta further you increase it, now you have a new theta 2 where theta 2 is greater than theta 1. Now you will require this level of change, delta lambda 2. This further at a shorter wavelength you can obtain diffuse reflection. Okay. So we can correlate it why we have a sun synchronous orbit to place the satellites to see the Earth's surface. So sun synchronous orbit means the satellite is always seeing those places where there is a midday. I'm giving you, this is also in a kind of assignment or homework to read about sun synchronous orbit.
Sir, sir, if this surface is perfect white ice, then more than 90% will be radiated back, even if the height is more.
Pardon?
Sir,
This is
if
not,
this
see, this is not a height. This is a standard deviation. This is a roughness. Roughness का meaning I think इधर मैंने बताया था ना यहाँ पे. I hope you understood. Hello.
yes, sir. Sir, even if it is slightly rough, still most of the light will be radiated back, reflected back, if it is near white ice.
No, see, fine. Okay, you are talking about ice as a kind of Earth surface object.
Yes,
So
sir, North Pole or South Pole.
that is what you want to conclude over here.
No, sir, asking will the equation hold true?
This equation hold true for all the objects. Just see this sun synchronous orbit. Kindly read about this orbit and also the reason why for the satellite imaging we place satellites in sun synchronous orbit. Fine. Okay. So again, I am giving you 5 minutes time to note this discussion in your notebook. Write it in your notebook. Okay, so now based on this discussion, how we distinguish between two objects using remote sensing. Okay. Okay. So what do we mean, or what is our aim behind the remote sensing? Our aim behind the remote sensing is to acquire the geo information in terms of images. Okay. And by analyzing the images, we need to identify the different objects. Okay. As well as we need to classify the objects. Okay. So do we have enough information in the images to distinguish the various features? Okay. So previously we talked about interaction with the Earth surface object. So besides the interaction, okay, the distinguish between these two various objects in the image, it also depends on the properties of sensor that we use. Okay. So what are the sensors we are using? What are the properties of sensors? Okay. And obviously we also consider over here the effect of atmosphere. So radiometric resolution of sensors we consider. Okay. And as well as the atmospheric scatter that we discussed previously, like how atmosphere behaves to the incoming radiation. Okay. There we'll see that due to the scattering, there we'll see that due to the scattering, the energy is absorbed. Okay. Energy is due to the scattering and absorption, the amplitude of energy decreases. Okay. When we consider the scattering over here, so due to the atmospheric scatter, as we discussed before, there are hedge in the image. So there is a hedginess in the image. Okay. And that is depends on the amount of scatter due to the scattering, and it increased the radiance received, and due to this there is a decrease in contrast of the image. Okay. And when we consider this radiometric resolution of sensor, there might be possibility like at a certain point, at a certain time, okay, that that particular ground resolution cell, okay, that is not recorded, okay, due to the malfunctioning of the sensor. Okay. So, and it also, okay, so there we talk about the measuring limit. So there are various types of resolutions that we define with images. Okay. So that we'll discuss. So let me know if there is any query. Shivam, could you please unmute?
Yes, sir.
So, what do you mean by this second point? Like when we are going to distinguish between two objects in the image, okay? So, what is the role of atmospheric scatter? First, tell me what do you mean by atmospheric scatter? What you know about it? Okay.
Sir, atmospheric scatter.
We discussed about scatters now when we were discussing about scattering effect in the atmosphere.
Sir, interaction between sunlight and particles in the atmosphere or any object in the atmosphere.
Correct. Due to interaction between EMR radiation with the particles or molecules in the atmosphere, this scattering takes place. Okay. And there we already discussed about the types of scattering, selective and non-selective. The selective we have Rayleigh scattering and Mie scattering, where we concluded that the dominant is the Rayleigh scattering. Okay. And if you remember, then we talked about due to the Rayleigh scattering, that there are two manifestations of Rayleigh scattering. The first one is the blue color of sky, and second one is a haze effect in the image. Just see over here. This is the first case. You know, you can just see this. It's a kind of layer over the image. Okay, while this is clear. So why this is layer over the image? This is called as haze effect. Okay, so when we collect the images, the atmospheric scatters also play a role to the quality of image. Okay. So with this two diagram, I will discuss about it. So what we talk, like the amount of scatter increases the radiance received, thus decreasing the contrast. This we need to discuss. First, we need to see why the amount of scatter, if it increases, then radiance received at the sensor increases. And why if the radiation, this radiance increased, okay? So why the contrast decreases? Okay, just see over here. If we select two grid, okay, one grid we are selecting over here, and the second at the same location I am selecting one grid over here. What happens? Like somewhere here the sensor is located. A particular spectral band, this sensor is designed, and it looks toward this. So what is the entire energy that is reflected back is seen over here. Okay, somewhere here we have a sun. So energy coming in this way. So just see over here. Now we are going to see that like the total radiance. Radiance means the amount of energy that is received over here. So that is total radiance received. What are the constituent in this radiance? Okay. What happened when there is an atmospheric scatter? Then let's say there are certain particles, they scatter energy in a different direction. Similarly over here, they scatter in the different direction. Like that. Okay. So due to the scattering also we have a energy component. They are the constituent which are received in the field of view of the sensor. Fine. So one component we have that is reflected from ground. Okay, that is from this grid over here. Okay, another component we are getting from the atmosphere, that is they are the atmospheric scatters. So see over here, if we change the another look, if we go to the another cell, another grid over here, so in this case also the atmospheric scatter will be same, but energy will be different. Fine, energy will be the different, reflected energy will be different, but constituent in the form of atmospheric scatters, they are same. Because nearly the atmosphere is same near about that this area when we consider this entire area over here. Okay, so what happens? The radiance means total amount of energy reaches at the sensor increases due to the atmospheric scatters. Okay, while in the second case, the scattering is very low. In this case, we consider and atmospheric scatters are low. So in that case, the radiance reaches the sensor is purely from the reflected component. Like if we see another grid over here, so purely the reflected component will reach to the sensor over here, the field of view of this sensor. Okay, so there is not a kind of constant addition of energy component from the atmosphere. Okay, like in this case, this layer you can see due to the equal energy constituent. Okay, in the all radiance component which are coming out from the ground resolution cell. Okay, so this is the reason why such kind of a layer, you can say it's uh, due to the equal energy added from the atmosphere, the radiance coming out from the cell. Okay, this kind of a layer can be seen. Okay, so this is the reason why we discuss over here. Atmospheric scatter has its role. Okay, and just see over here, due to this contrast, in this case there is more clarity, while in this case the image is not clear and it is hazy image. Okay, now the first part that I was discussing, like radiometric resolution of sensor. Okay, and the sensor may fail to record different radiance due to its measuring unit, sorry, measuring limit. I will discuss this part later on. Like in addition with radiometric resolution, we have three other resolutions also that we define with respect to the image. Okay. They are spatial resolution. You need to remember it. Spatial resolution. The second one is a spectral, while the third one is temporal. Okay. So we have four different types of resolution that determine the quality of image as well as talk about the processing. Like when we talk about temporal resolution, means how frequently we are acquiring the image from the same area. Let's say after each 15 days, we are acquiring the image from the same area, then we can say that temporal resolution is 15 days, and it is helpful in identifying the changes over that period. Okay. Spectral resolution is related to the wavelength in a particular band, while spatial resolution is size of this grid. Okay, I'm using many terms for this ground resolution cell grid. Okay, these terms are used for this smallest area unit on the ground. So this size, when we talk about it, is m into m. So this m is the resolution. Length of a side of a square block, smallest unit, for which we assign a unique DN number. This is the spatial resolution. So 10 minutes are left. I would like you to make note on this again, the discussion we have. And you can note down the queries in this particular discussion that will be taken up in the next lecture.